Okay, I'll just repeat myself. Hello, everyone. Thank you for joining us for best practices for schema evolution in Apache Iceberg, making your data future proof. My name is Abba, and I'll be your moderator for the session. Just a heads up that we will have a brief live Q&A after the presentation, so be sure to use the Ask a Presenter tab to ask questions and engage with your fellow attendees. With that, I'd like to welcome our speaker, Rajesh with PRA Group to the stage right now. Take it away.
Thank you, Abba. Sorry for jumping in little early. Hey everyone, good afternoon, good morning, good evening, wherever you're in the globe. So my name is Rajesh. So today I'm here to talk about best practices for schema evolution in Apache Iceberg. I have like 10 years of experience working in the data management domain. So where I worked with multiple clients that do businesses in financial sector, transportation and logistics. So my core skill set is creating the databases either on-prem or on the cloud, and helping our internal teams like these reporting teams with the reporting and analytical needs. So let's get started with this presentation. So here is our roadmap for today's discussion. We will look at the pain points associated with traditional schema management and how they impact businesses handling large volumes of data. Then we will start with a quick introduction to Apache Iceberg, its key features and why it was created. Next, we will deep dive into how Iceberg handles schema evolution, focusing on its metadata-driven approach, which allows schema changes without rewriting entire tables. So this is one of the core strengths of the Iceberg compared to older data lake formats. We will then go into a practical best practices for handling schema changes, covering scenarios like adding new columns, modifying data types, renaming and dropping columns. I will provide real-world examples of when and how to apply these changes without affecting existing queries or breaking production workloads. After that, we will discuss performance considerations, such as how Iceberg partitioning and column pruning mechanism ensure that schema changes don't slow down queries. We will also look at a schema versioning and rollback mechanisms, which are essential for ensuring stability when making modifications. I will then share a real-world case study of how a large company successfully implemented Iceberg for schema evolution at scale, solving challenges related to schema flexibility and query performance. We will finish with governance best practices, ensuring schema changes are well documented and monitored for compliance and efficiency. Finally, we will wrap up with Q&A session where you can ask questions. So let's get started. So challenges with traditional schema management. So schema evaluation has historically been a nightmare in traditional databases and data lakes. So let's take a real world example. Suppose you are running an e-commerce platform and want to add a new field for tracking customer referral codes. In a traditional database, this simple change could require locking tables, migrating existing data, and updating all required queries. So let's see like some of the serial bottlenecks, for many data teams with the schema management. So first, even a simple rename or column drop can be catastrophic, breaking downstream dashboards, pipelines, and applications without warning. Second, many traditional systems still require table logs or even downtime just to apply a schema change. And that is unacceptable in today's fast forwarding world. So then there is the manual overhead. You need to write scripts, test in multiple environments, and often coordinate across teams. It's not only time consuming, it's risky. So what's worse, there is as usually no version control. So if a change breaks something, good luck, rolling back or figuring out what changed. So we also face schema drifts where dev, test, and production environments slowly go out of sync. So this silently erodes data quality and trust. Add to that the lack of an audit trail. So there is no visibility into who changed, what, when, or why. So a huge concern for compliance, heavy industries. So data consumers and producers are often tightly coupled, meaning one small change can force everyone to update their systems, killing agility. And when it comes to modern formats like JSON or nested data, traditional schema tools just can't keep up. They are designed for rigid, structured data. So the end result, teams get slower, more cautious, and less innovative, all because they fear breaking the system with a schema change. So the schema change frequency across organizations. So this chart illustrates the average frequency of schema changes across different type of organizations measured in changes per quarter. As expected, startups and agile tech company lead the pack, often changing their schemas weekly or even daily. They prioritize speed, new features, and experimentation, so schema flexibility is crucial. Mid-sized enterprises tend to evolve their data models on a bi-weekly or monthly basis, as usually aligned with sprint cycles. For large enterprises and financial institutions, schema changes are more structured and go through formal review processes, which slow down the pace to quarterly. Finally, in highly regulated sectors like government, healthcare, or defense, schema changes are rare and heavily audited, typically 2 to 4 times a year or even less. So this trend shows why modern table formats like Apache Iceberg are gaining traction because they allow safe, incremental schema evolution without downtime, which is critical across all these tiers. So in this slide, we'll cover about introduction to Apache Iceberg. So Apache Iceberg is an open source table format designed for large scale data lakes. It was developed at Netflix to address key limitations of existing data formats like Apache Hive and Apache Parquet. So Iceberg is a set of APIs and libraries for interaction with this specification, allowing other engines and tools to integrate with Iceberg tables. Iceberg isn't a storage engine, nor an execution engine, nor a service. So the development of Apache Iceberg was driven by Netflix goals, so which includes ensuring table correctness and consistency, enabling faster query planning and execution, allowing users to focus on logical data management rather than physical layout, supporting table evolution, example schema changes seamlessly, scaling these capabilities to handle Netflix vast data sets. So what makes Iceberg unique? First, it allows schema evolution without breaking queries. So unlike traditional databases, where adding or modifying a column often requires expensive data migration, Iceberg separates metadata from data storage, allowing you to evolve schema safely and efficiently. Another major benefit is ACID transactions, ensuring consistency and integrity across massive data sets. This is crucial for analytics and machine learning applications where frequent data updates occur. Additionally, Iceberg supports time travel queries, meaning you can access previous versions of data. This feature is essential for debugging, regulatory compliance, and auditing, as it allows organizations to track historical changes effortlessly. Iceberg is optimized for performance and scalability. Features like partition pruning, column pruning, and vectorized reads make query faster and more efficient, even on petabytes of scale of data sets. And Iceberg also have engine capability. So Iceberg is not locked to a single engine, whether you're using Spark, Flink, Trino, or Presto, it just work across your stack. And it is also cloud optimized, so built from the ground up for object stores like S3, GCS, and ADLS. Iceberg scales effortlessly in modern data lake environment. So Iceberg is built for modern data teams to enhance the scalability, the flexibility, and future proof. So let's take a look at the Apache Iceberg architecture. So Apache Iceberg isn't just a table format. It's an intelligent data architecture purpose built for modern analytics at scale. So let's explore the three core layers that makes it so powerful. So the first one is the data layer, where your data lives. At the foundation, we have the data layer. This is where Iceberg stores your actual information. So data files use highly optimized formats like Parquet or ORC to store large-scale data, analytical data. Delete files are a game changer. They track row-level deletes without rewriting files, enabling efficient updates and true mutable tables on immutable storage. This allows Iceberg to support fast, scalable operations without data duplication or reprocessing. So the second layer is the metadata layer. So this is called the brain of the system. So now here where Iceberg really shines, it's three-tier metadata system. So the first one is a manifest files, acts as smart indexes, tracking file level stats like partition ranges, row counts, and maximum values, enabling blazing fast query pruning. The second one is the manifest list, groups these manifest files into point in time snapshots. This is your versioned view of tables. So the third one is the metadata files or the control center, tracking schemas, partition strategies, current and past snapshots, and lineage. So this metadata driven architecture powers Iceberg famous features like schema evolution, time travel, and rollback. So the third one is the catalog layer. So this is also called the traffic controller. So the catalog layer sits at the top. This is what connects everything together. It holds a pointer to the current metadata file. So any engine, Spark, Flink, Trino always reads a consistent snapshot. It ensures transactional safety across distributed systems by integrating with the trusted services like Hive Metastore, AWS Glue, Project Nessus, or Postgre. Think of it as the source of truth that guarantees consistency even in multi-engine, multi-user environment. So in summary, Iceberg architecture delivers what traditional systems cannot, that is like scalability, flexibility, and analytics on data lakes. It's how you enable features like schema evolution, time travel, asset transactions, and more without compromise. So in this slide, we will cover the schema evolution for Iceberg. So now that we have discussed the challenges of the schema management and the Apache Iceberg introduction and the Iceberg architecture, let's explore how Iceberg solves these problems with a completely new approach. So one of the most powerful features of Iceberg is its metadata-driven schema evolution. Unlike traditional systems that require physical modifying stored data, Iceberg stores schema changes at the metadata level. So this means when we add, rename, or drop columns, we do not need to rewrite the entire data set, only the metadata is updated, making the process incredibly fast and efficient. Another major advantage is backward and forward compatibility. In a traditional database, if you modify a schema, you might break older queries or force users to adjust their applications. But in Iceberg, schema evolution ensures that older queries still function correctly even after changes are made. So additionally, Iceberg maintains schema snapshots, which means you can roll back to an earlier version at any time. This is extremely useful when debugging issues, conducting audits, or ensuring compliance with regulatory requirements. For example, let's say you mistakenly deleted a column that was still being used by some reports. In a traditional system, recovering this data could be costly and time consuming or even impossible. However, with Iceberg snapshot functionality, you can instantly revert to a previous schema version, avoiding major disruptions. So one of the standout feature of Iceberg is its ability to evolve schema and partition strategies without rewriting data. So this means that changes in business requirements or data models can be accommodated without significant disruption to existing workflows, offering flexibility that traditional table formats struggle to provide. This metadata approach makes Iceberg a game changer for large-scale data lakes, analytics, and machine learning pipelines. So now that we have covered the theoretical part, let's move on to the practical aspects, how to apply schema changes in Iceberg safely and efficiently. Okay, so there is one more slide about the schema evolution specifically. So the schema evolution is a core enabler of flexibility in the modern data systems like Apache Iceberg. So as businesses evolve, so do their data needs. So new features, new metrics, new regulations, all of these require changes to the data model. So without schema evolution, every change, no matter how small, could result in pipeline failures, reprocessing of massive data sets, or manual intervention across multiple teams. So schema evolution allows you to make safe, incremental changes to your data schema without retrieving data or disrupting users. This includes adding new columns, renaming existing fields, or even restructuring tables, all while preserving access to historical data. It ensures continuity in analytics, so teams relying on dashboards, reports, or ML models won't experience sudden breakages. And importantly, it helps avoid the data swamp effect where data lakes become too rigid or too messy to trust. So in a real world example, so let's say we launch a new product and start capturing a new customer behavior metric, user engagement score. So with Iceberg schema evolution, you can simply add that field and your existing data stays intact. So no downtime, no full table rewrites, no broken reports. So in summary, schema evaluation is about keeping your data agile, analytical, continuous, and governance intact, even as everything else changes. Okay, so what are the types of schema changes? So the schema evolution in Apache Iceberg is not just flexible, it's also powerful. But with power comes responsibility. So let's explore what we can change and how to do it safely and smartly. So the first one is add columns, the safest change you can make. So you can add fields at any time and Iceberg handles it gracefully. So all the data will simply have null or default values. The second one is drop columns. We have to be a little cautious about this. Yes, we can drop columns, but first make sure no downstream jobs, reports, or consumers still depend on them. A dropped column is gone for good, so we have to always double check dependencies. So the third one is rename column. So it is metadata safe, operationally risky. So Iceberg supports safe renaming in the metadata layer, but tools like Spark, Flink, or BI dashboards may match by name, not ID. So use rename sparingly and communicate across teams. So the fourth one is reorder columns. So this is like a cosmetic only change. So reordering does not affect data layout or performance, only logical structure. So this is used for cleanup or aligning schemas across tables. So it will not have any impact on queries. So the last one is change column types. So this one we have to avoid if possible. This is the riskiest change. It can break any downstream tools. So the best practice for this one is to add a new column with the correct type and deprecate the old one. So the final takeaway is, so Iceberg gives you next generation schema evolution, but to truly unlock its power, we have to follow the best practices. So think of schema changes as product releases, not just technical updates. So let's go over an example or a scenario about adding a new column. So adding a new column is one of the most common schema changes in any database system. Whether you're tracking a new customer attribute, a business metric, or a product feature, new columns need to be added over time. However, in traditional databases, adding a column often requires a full table rewrite, causing downtime and increasing storage costs. So with Apache Iceberg, adding a new column is incredibly simple because it's metadata driven. You can introduce a new column without rewriting existing data. This means queries that do not reference the new column will continue functioning without modifications. So but there are still few best practices to follow to ensure a smooth schema evolution. So the first one is using the meaningful column names. So column names should be descriptive and future proof. Instead of something like COL1, use something like customer referral code. Avoid being vague or generic names that may require renaming later. So the second one is set a default values where necessary. So if a new column is essential for future queries, ensure it has a default value so that old records do not introduce null related issues. So if your query logic assumes a column will always contain values, so a missing or null value can cause unexpected results. Then we can monitor the downstream dependencies. So although adding columns do not break queries, We have to be aware of any BI tools, dashboards, or ETL processes that may need updates to take advantage of the new column. So we have to communicate the change across the teams, inform data consumers about the new column and its intended use, and update documentation or data contracts or agreements where needed. And also, we don't need to solely rely on the column names, because Iceberg tracks columns by unique field IDs, not just names. So ensure that IDs are preserved and distinct, especially in multi-team environments. So we have to keep the change additive. So do not modify or drop other fields at the same time. Add columns in isolated comments when possible. So this will make your life easier when making the rollback. And if you're doing any impact early analysis, later, that's going to help you. So this ability to add columns seamlessly is a major advantage of Iceberg or traditional data lakes. So you can see some sample code there about adding columns, and then how we can update the column metadata by setting default values. So now let's discuss a scenario for the data type change. So changing a data type might seem simple, but it's one of the most sensitive schema modifications, because it can lead to data loss or unintended query failures. However, data type conversions are limited. For instance, changing a column from int to string isn't directly supported and requires careful handling. So for example, consider a table where customer ID were initially stored as int, but due to the business growth, the company realized they needed a big int to store more values. So this is a safe conversion, because an int can be upgraded to a big int without loss. However, some type conversions are dangerous. If you change a column from float to some binary, so decimal values will be rounded off, or if you change a data type from float to int, so we might have some data loss and inaccurate reporting. So another the risky conversion is reducing the field length in string or varchar, so which can truncate values and cause missing data. So to ensure safe data type changes, we have to follow a few best practices. So first we have to assess the compatibility. So ensure the new data type is compatible with the existing one. Example, int to long, float to double. Rather, we have to avoid changes that could cause loss of precision, truncation, or parsing errors. Example, string to binary. And then we have to sometimes go for a temporary dual column approach. Prefer adding a new column, so rather than changing an existing data type, we can add a new column with a desired type. So this preserves historical context and avoid backward compatibility issues. Then we can test with any sample data that we may have, like run sample queries and test joins, filters, and aggregations using both the old and new type. So validate schema compatibility using Spark, Flink, or Trino, or whatever engine, that we can use, and we can also consider data rewrites if needed, So for major type changes, we may need to rewrite historical data or backfill to ensure consistency. So we have to plan this as a separate and well-scoped migration task, So changing data types require careful planning, but is much easier with Iceberg than traditional databases. So now let's take a look at the important type of schema evolution, which is renaming and dropping columns. So renaming and dropping columns are common schema changes, but they require more cautious compared to adding or modifying data types. If done incorrectly, they can break queries, dashboards, and downstream applications. So you can drop columns from the schema. The data for the dropped column will be removed, but this operation is typically performed with caution to avoid data loss. So let's start with renaming columns. Suppose a company has a column called cust ID. but they want to make it more descriptive by changing it to customer ID. So in a traditional database, renaming a column could break queries that reference cust ID, requiring updates across all dependent scripts, reports, and applications. However, in Apache Iceberg, renaming a column is metadata driven, meaning the underlying data remains unchanged. The change is applied at the metadata level, allowing for instant updates without table rewrites. But any SQL queries or BI dashboards referring the old column will need updates. So one of few best practices for renaming columns is to communicate schema changes to all the teams using the tables, check dependencies prior to making a change, and use versioning to track changes and provide rollback if needed. So now let's talk about dropping columns, which is a permanent change. So for example, let's say a company no longer needs the last login date because they have switched to a different user tracking system. So deleting this column in Apache Iceberg removes it from the metadata, but the actual data remains intact in the previous snapshots. This means you can not undo a drop operation unless you restore from an older snapshot. So few best practices for dropping the column is double check that no applications rely on column before removing it, archive or backup the data before deletion, or use Iceberg snapshots to restore older versions if needed. Renaming is a safe schema evolution practice, but dropping columns should be done with extreme caution to avoid losing critical data. So now let's look at how schema changes impact query performance. Oh, we are going to the best practice. Okay, so let's look at the best practices then. So for Apache Iceberg, it gives us a modern and flexible way to evolve data schemas, but we can only achieve the real power with some best practices. So the first one is plan for future growth. So don't design your schema just for what you need today. So think about where the data might go. Will you introduce new customer metrics, capture behavioral signals, add consent tracking for compliance? So Iceberg makes changes easy, but planning ahead means fewer headaches down the road. So we have to design for change, not just for now. So use meaningful default values. So when adding new columns, avoid dumping in empty or null values unless you have to. So instead, provide a default that actually makes sense, like unknown, zero, or a placeholder region. So this keeps your data clean, consistent, and and analytical use perspective. So a thoughtful default today prevents confusion tomorrow. So then communicate schema changes. So this is big. So schema changes aren't just for engineers; they impact analysts, BI teams, machine learning pipelines, and stakeholders. So if you don't communicate, someone's dashboard or job will break, and this and eventually they might lose the trust on the data. So we have to treat schema changes like product releases, and we have to announce them. So then version control the schemas, schema changes should be tracked like code. So we can use a GitHub or a schema registry. So we can see like who changed what, when, and why. So if something breaks or does not match expectations, so we can roll back or at least audit, and Iceberg supports that if you track it properly. Then we can test thoroughly before production. So always validate schema changes in a staging environment. So with real queries, dashboards, and consumer systems. So what looks fine in metadata can break pipelines or corrupt joins in practice. So test first, deploy with confidence. So production isn't a place to find out something broke. So schema evolution is one of the Iceberg superpower, but it only works when handled it strategically and carefully. So these practices are what make schema changes safe, scalable, stress-free, even in complex enterprise environments. So here are some of the key benefits of schema evolution. So the first one is flexibility. So easily adopt to evolving business needs without disrupting existing data or queries. and then performance, so eliminate the need for expensive full table rewrites during schema changes. And it also provides the backward compatibility with older schema versions and minimizing disruptions. And by applying schema updates using straightforward SQL commands, so no complex migration required. It's very simple to implement. So as per the Databricks survey in 2023, companies that are using Apache Iceberg are similar, for their flexible data modeling approaches, so they have seen accelerating time to market their products by 35% and boosting their data team productivity by 40%, And also let's take a look at the business level impact, So from a business standpoint, they can have like a faster innovation, quickly evolving data models, empower teams to prototype and deploy new features or products with agility, and reduced operational cost, avoiding costly data migrations and system downtime translates into substantial savings and improved data quality. So schema flexibility enables more accurate modeling of real world entities and enhanced collaborations. When teams can easily adjust the schema, adding or modifying tables, they are more likely to experiment, share ideas, and drive innovation together. So what are some of the challenges of implementing schema evolution? So the first one is schema drift, So untracked changes lead to inconsistencies, query failures, and inaccurate reports, So we have to track schema versions using Apache Iceberg metadata. So then we have data compatibility. Even small changes can break down downstream systems, So we have to use staging and validation to catch issues early. Then we have governance. So strong flexibility requires strong governance. So we have to enforce schema policies and conduct regular audits, And the most important one is training. So the teams should equip with best practices to prevent common schema evolution mistakes, And then also the tool compatibility, So verify that all the data tools and pipelines, support Iceberg and can handle evolving schemas smoothly. So let's see like what is backward and forward compatibility. So backward and forward compatibility are essential aspects of schema evolution. So backward compatibility ensures that old queries remain functional even when the schema is updated. For example, if a new column is added, but older applications are unaware of it, they can continue querying unaffected. So this allows organizations to roll out schema updates gradually without disrupting critical operations, And forward compatibility, on the other hand, so ensures that newer queries can read older data, even if the data scheme has changed. So this is particularly useful for maintaining long-term data sets, so that may undergo multiple schema revisions. So Apache Iceberg achieves this using a metadata layer that tracks schema versions, So for example, if a company adds a customer loyalty score field to its schema, forward compatibility ensures older data without this field won't cause any query failures, So this flexibility is essential for large organizations managing diverse data sources, so ensuring both legacy applications and modern analytical tools operate seamlessly. Okay, so what are some of the performance considerations? So one of the biggest concern when evaluating schemas is performance impact. So in traditional databases, modifying a schema often requires rewriting tables, which can significantly slow down query performance. So however, in Iceberg is designed to minimize these impacts and can keep queries faster, even after schema changes, So how we can do it is metadata driven updates, prevent table redirects, So unlike the traditional data lakes, so in Iceberg, we are using, we are not rewriting the tables, rather we are using the schema changes, applying the schema changes at the metadata level. So this means we can make any type of schema changes without touching the existing data files. So ensuring the instant changes, with no downtime. And then, we can use the partition pruning first for faster queries. So let's take an example. So imagine a company has a sales data partition by region and year. So when a query asks for sales data for 2023, Iceberg automatically ignores the older partitions, so reducing the amount of time scanned or amount of data that is scanned. So this makes query significantly faster than traditional data formats. And then we can also do the column pruning for optimized reads. So column pruning is another powerful performance feature. So suppose we have a customer orders table with 50 columns, but your query only selects order ID and order date. So instead of scanning the entire data set, Iceberg retrieves only the columns referenced in the query. So this will reduce the IO operations and improve efficiency. So this means that even as the schema evolves over time, so queries remain fast and efficient because Iceberg reads only the necessary partitions and columns by leveraging metadata-driven changes. So a schema evolution with partitioning. So partitioning is a critical optimization technique that improves query performance by limiting the amount of data scanned. So Apache Iceberg takes partitioning further with its dynamic partitioning feature. So Iceberg allows partitions to be added or modified without the need of manual reconfiguration. So additionally, Iceberg supports the partition pruning with which further minimizes data scanning. So this is particularly beneficial for companies that are dealing with the petabytes or terabytes of data. By reducing their query times, companies save on compute cost and deliver analytical insight faster. So implementing effective partitioning strategies is a key best practice for maintaining query performance while supporting schema evaluation. So mechanism. So one of the biggest risks with schema changes is making a mistake, so that breaks the critical workflows. So every schema change in Iceberg creates a new version of tables metadata. So this means if something goes wrong, you can simply revert to an earlier version without losing data. And some of the best practices for schema versioning is using Iceberg snapshot-based versioning to track changes safely. And before applying major schema changes, test them on a non-production environment and document every schema to ensure the team understands the modifications. These are some of the best practices that we can apply for schema versioning. So now let's look at a case study. So as you all know, Airbnb, which is a global online marketplace that facilitates short and long-term homestays and experiences, and they do earn commissions from each booking, right? So basically, they have achieved real-time analytics using the schema evolution. So as you know, Airbnb processes massive volumes of data for use cases like search behavior analysis, fraud detection, pricing optimization, and more. So as a data-driven organization, Airbnb's data models evolve constantly to support new products, features, and they do some experiments and they have to comply with the regulatory needs. So this motivated the Airbnb team to upgrade its data warehouse infrastructure to a new stack based on Apache Iceberg. So what it helped the organization is that Apache's Iceberg partition information is not stored in the Hive metastore, so that reduced a large amount of load from it. And Apache Iceberg tables does not require S3 listings, so which remove the list after write consistency requirement, and in turn eliminate the latency of the list operation. And Iceberg spec defines a standard table schema, so guaranteed consistent behavior across compute engines. So all in all, Airbnb experienced a 50% compute resource saving and a 40% job elapsed time reduction in its data ingestion framework with Iceberg and other open source technologies. So and then Netflix, so Netflix is one of the key company that played a crucial part in the Apache Iceberg, by implementing Apache Iceberg, Netflix was able to make schema changes seamlessly and ensuring that existing queries didn't break. They also benefited from Iceberg time travel capabilities, allowing them to roll back schema changes. So this is one of the real world example highlighting how Iceberg can handle large scale schema evolution challenges while maintaining efficiency and query stability. So I have a few more slides, but I see that we are running at the top of the hour. So I'll just quickly run through, so I have a slide that talks about governance and schema management best practices, about from a governance standpoint, what are some of the things that we have to do when we are working on schema management. We can validate before deployment, we can track changes with schema registries, we can maintain version control for audits, and also enable the rollback with time travel. And then I have a slide that talks about monitoring and managing schema evolution. What type of monitoring tools or techniques that we can use to monitor the schema evolution, and how can we monitor the key metrics, like performance, query performance, or data growth, or the schema compatibility, and so on and so forth. And also, the security and compliance is a crucial aspect of it. So we have to enforce the access controls, who can do what changes, and how to protect the sensitive data, and how we can use the time travel, for any auditing purposes like GDPR, HIPAA, and for any SOX compliance standards. Um, and then what is the future of schema evaluation? As we have seen AI in pretty much in every industry, so eventually, we can see AI driven schema management, that can predict schema changes. And we can also look at self optimizing schemas, which can help or enhance the data quality. And what are some of the common mistakes, during the schema evaluation. So if we don't do proper testing, a lack of version controls, and applying change directly in production without testing is also risky. So for some of the final recommendations is leverage Iceberg schema evolution capabilities, and also you can implement backward and forward compatibility, and to monitor and manage schema changes effectively, and follow best practices to maintain the data integrity. So I have added few links in my presentation, where you can look at and more if you want to deep dive into more detailed technical discussion, or so you will be able to look at the sample code as well here. So I would like to thank you all for attending this session, and I would like to also thank the selection committee, for selecting my session. So I'll give it back to Abba. And any questions?
Hi, thank you so much, Rajesh. So we have one question. Can schema evolution break query performance, and how do you detect it?
Yes, changes like adding wide columns or modifying partition fields, can impact the file pruning, scan planning, and query speed. So we can detect it by, tracking query latency, and scan the file count. So using Iceberg metrics and Spark execution plans, we can also analyze the performance drops, and rolling back, if there is some degradation within the logs is observed.
Okay. So that's all the time we have for questions. We are under 1 minute now. Thank you so much for joining us, Rajesh. As a reminder, all the sessions will be available on demand within 1 hour of the end of the event. So thank you once again. Up next in track 2, we have leveraging Iceberg for AI BI workloads at Rednote with Chao or Simon Sun at Rednote. So see you out there. Thank you.
Thank you.